Welcome to Curbing the Curve, assessing socioeconomic factors in COVID-19 risk rates for the purposes of increased resource allocation. Dr. Anthony Fauci recently said, "The cavalry is coming, but don't put your weapons down. You better keep fighting because they're not here yet," in regards to COVID-19. In that spirit, the Roche Data Science Coalition is asking for help from across the AI community with what they're calling the Uncover Challenge, which seeks to identify which populations are at greatest risk for contracting COVID. This dovetails well with my own research interests. While we wait on a vaccine, where should we be funneling resources to lessen the impact of the expected third wave? But before we get there, let's understand the current state. 1 in 50 Americans have contracted the coronavirus so far, and 1 in every 2,000 have died of it. Here we can see a county map of the United States. Everywhere indicated with red have a worse rate than that 1 in 50 and 1 in 2,000. Everywhere in blue have a better rate in both that 1 in 50 and 1 in every 2,000. Yellow is above with one and below in the other. These reds and blues are what I plan to use for the basis of my investigation. Ultimately, I ended up using logistic regression with cross-validation to do this. But first, let's actually talk about my process. Luckily, the Uncover Act has an amazing data set that I was able to use as a launching point. I was then able to run several models in order to pick the right one. I threw my data in to see what would happen, and then scaled everything from 0 to 1. After all, if some of my numbers are zeros and ones and others are all in the millions, that's not really helpful. It's not comparing apples to apples. Next up, I looked at polynomial features. What would happen if I looked at factor A times factor B? Would that be a more telling number? Then I used something known as lasso regularization to get rid of everything that didn't add value to my model before looking at variance thresholds. For example, if the range of numbers isn't that large for a column, it might not be the best predictor. And finally, I did parameter tuning, which is all that tinkering at the very end to make sure the model is close to perfect. Before we look at the results, let's understand how we know that I'm confident about this model. First of all, at looking at low risk rates, or what are known as zeros, I looked at precision, or what percent of the negatives are actually negative. In this case, the precision tells us that the model will incorrectly identify a county as at risk 7% of the time. On the flip side, for high risk rates, I looked at recall. That can be thought of as what percent of positives, or at risk, are correctly identified. The model will correctly identify at-risk counties 97% of the time. Finally is R squared. At 83.1%, what that tells us is 16.9% of the differences between high-risk and low-risk counties could not be explained by the data. So let's take a look at the actual results. First off, here are the 30 features with the highest and lowest average coefficients. Now, to understand coefficients, they show the impact of a measure on the model. A positive coefficient, for example, teen birth rate, means that the higher that teen birth rate becomes, the higher that the risk for that county becomes. A negative coefficient, for example, percent uninsured, has the opposite effect. The lower a percent uninsured becomes, the higher the risk. The top 30 features with the highest and lowest average absolute value of their coefficient is a way of understanding, without looking at positive and negatives, how do all of these stack up? For example, you'll notice that percent uninsured, when flipped over to a positive, is the fourth most important factor, when it was the most important when it was a negative coefficient. This just helps me, again, compare apples to apples. Next, I looked at features by number of times used in the model. The more that something is used in the model, this might suggest that it has a lot of really good feature interactions and may or may not have a lot of value on its own. When we look at the predicted probability of high risk from COVID as a result of the model, what we see is a lot of reds, which indicate a high probability in the American South and parts of the Northeast, versus blues and light greens, which indicate a lower probability of that high risk from COVID-19 throughout the plains and the Midwest. However, when we look at the map, we see that this doesn't catch the current prevalence of the virus in the Midwest or the plain states. I have a hunch that this leads to our first finding, not to underestimate the impact of partisanship. In the 2020 election, many of these states and counties leaned or heavily favored the Republican Party, which has made this a very partisan issue. My second finding is it's important that we issue stay-at-home orders. A failure to issue stay-at-home orders negate certain protective factors. So, stay-at-home orders are amongst the most highly used features. The average coefficient, however, is close to 0, meaning these features rely on interactions with other features to impact the model. And a negative coefficient means it mostly is impacting the protective features. Stay-at-home orders are binary 0 to 1 scores, which means that whenever you multiply 0 times a protective factor, it comes out as a 0, meaning that factor is negated. I also found that we need to focus on areas of extreme poverty because many of the underlying risk factors are positively correlated with poverty. So for example, high teen birth rate leads to higher risk. High percent smokers leads to higher risk. Severe housing cost burden leads to higher risk. Percent food insecure leads to higher risk. So these are just fascinating interactions that I think that we do need to take a closer look at. In terms of future research, I do think it's important that we look at how politics interact with the risk rates, as well as climate. What is the impact of climate? Does the cold weather versus warm weather impact risk rates at all? And finally, I want to take a look at the best interventions for high-risk areas. For example, analyses should be conducted to determine what might most effectively mitigate identified risk factors, such as increased access to health resources, increased access to virus and pandemic education, or improved social safety programs. We may have answered the where, but not necessarily the how. That's all for now, but I do hope to do more research on this area. Thank you so much for your time.